We're going to start this section on dividing a polynomial by a monomial by reminding ourselves how to do division in general using just numbers. If I say divide 325 by 5, you might think of it one of a couple of different ways. Some of us will put 325 in the top of a fraction, and then we'll think 5 goes into 32. Well, it doesn't go in evenly, but it goes in 6 times with a remainder. And that remainder is 2. 5 times 6 is 30, and the remainder is 2. Then we say 5 goes into 25 5 times. Here's my answer. 325 divided by 5 is 65. Others of us will resort to what we call long division. Notice when we do this, though, the number we're dividing up, as it were, goes inside, and the number we're dividing by goes outside. 5 goes into 32, not evenly, but it goes in 6 times with a remainder of 2. Instead of just writing the remainder down this time, though, I'm going to multiply 6 by 5 and write the result here. Then I'm going to subtract this number from this number. 32 minus 30 is 2. The next step is to bring down the next digit in the problem, in this case, 5. And then I can start over. 5 goes into 32 6 times. 5 goes into 25 5 times. Multiply again, 5 times 5 is 25. Subtract again, this time we get 0. My answer is the number I ended up with on the top here, 65. This problem's a bit strange. You wouldn't actually normally see a division question written this way. If I want to divide this number by 5, I just add these together and then divide the result by 5. But I'm going to do it this way anyway because I want to make a point. A couple of points, actually. First of all, I want to remind you that reducing this fraction this way is incomplete. 5 goes into 5 once, 5 goes into 15 3 times. But this is not equal to 10 plus 3. How do I know? Well, in addition to telling me to divide, this fraction bar is keeping this sum together. In other words, I should do this first, if I can. 10 plus 15 is 25. If I do that first and then divide by 5, I get 5, not 13. Do you remember how we dealt with this problem before? We said that if we're going to cancel in a fraction with a plus sign in it, or a minus sign, then whatever you cancel, you have to cancel from down here and both terms up here. 5 goes into 5 once, 5 goes into 15 3 times, 5 goes into 10 2 times. Now these are added together, so if I add 2 plus 3, and I get 5 over 1. 5 over 1 is 5. So this did not work because I canceled this 5 and a copy of 5 from the 15, but I had not canceled a copy of 5 from the 10. That's how I ended up with 13 instead. You can clearly see here that the answer should be 5 and not 13. All right, now that I've reminded you of that, let's take a look at how this looks in long division. Again, we wouldn't normally see a problem like this. We'd add these together and divide that sum by 5. But we can do it this way. It may feel a little awkward, but it is possible, and it's going to come in really handy. Now, we already know the answer here is 5. We've tried it 3 different ways, 1 that we know is not correct, and 2 other ways that are correct. So we know the answer is 5. Let's take a look at doing it by long division. 5 goes into 10 twice. Just ignore the rest of this problem for right now. 5 goes into 10 twice, and 2 times 5 is 10. Subtract, and then bring down plus 15. 0 plus 15 is 15, so I don't really need the 0 plus part. Now that I've brought down my next number, I can start over. 5 goes into 15 3 times. But this is a sum. 5 goes into this sum. And so this plus sign needs to be represented in the answer as well. And lo and behold, I get 5. Now, you don't need to do long division this way, but we are going to be doing long division using polynomials. I'll introduce it in this section, and in the next section it's going to become essential. Okay, here's our first problem. Divide the polynomial 10x cubed minus 15x squared by 5. This is the same problem twice. We're going to do it once by rewriting it as a fraction, and then we'll do it using long division. Remember what I said about canceling when there's a plus or a minus in the numerator or the denominator of your fraction. We can't just cancel this 5 with this 15. We have to cancel it with the 15 and with the 10. I can do that though. 5 goes into 5 once. 5 goes into 10 twice. 5 goes into 15 3 times. What about the x's? Well, 5 doesn't go into x. So that's really all I can do with this. I can rewrite it as 2 times x cubed minus 3 times x squared over 1. Only I don't need the over 1 part. This is my final answer. Let's do the same problem by long division. 5 goes into, what do I need to multiply 5 by to get not just 10, but 10x cubed? 5 times what? 5 times what equals 10x cubed? Well, the 5 times 2 is going to give me the 10, but I need to multiply it also by x cubed. Now when I do my multiplication, I get 2 times 5 is 10, and x cubed, and then I can subtract. In long division of polynomials, I'm never going to subtract in the strictest sense of the word. It's not as critical here. It's pretty obvious to see that 10x cubed minus 10x cubed is 0. But to clarify things as we go along, I'm going to say change all the signs in this line. Here we only have one term in this line, but in the future it will be handy to say change all the signs in this line and then think addition. 10x cubed plus negative 10x cubed is 0. Having done that step, I'm going to bring down the next piece. And in this case, remember I have to bring the sign down with it. So it's bring down minus 15x squared. 0 minus, well, I don't need the 0 part, do I? So I'll erase that, again, just for clarity. Now I get to start over. 5 goes into, what that means is, what do I need to multiply by 5 to get negative 15x squared? Well, to get negative 15, I need to multiply 5 by negative 3. But this would just give me negative 3 times 5 is negative 15. What about the x squared? I need to multiply 5 by negative 3x squared to get negative 15x squared. Now that I've determined that, let's do this multiplication. Negative 3x squared times 5 is negative 15x squared. When I subtract, I get 0. So this is my answer. 2x cubed minus 3x squared. Notice that my answers match. This is the same problem done two different ways, but it's the same question, so I should have the same answer. I'd like to do this problem again, but instead of just dividing by 5, let's divide by 5x. And this is actually the first example in your textbook. Okay, here we go. If it's written as a fraction, division is really a case of canceling. I can start out the way I did before. 5 goes into 5 once, 5 goes into 15 3 times, and 5 goes into 10 twice. But there's more to it this time. I still have an x down here, and I have x's in the numerator as well. This minus sign here tells me I have to cancel not just with one of these terms, but with both of the terms on the top. X goes into x one time. X goes into x squared. What do I need to multiply by x to get x squared? I need to multiply x by x to get x squared. Like I need to multiply 5 by 3 to get 15, so 5 goes into 15 3 times. I need to multiply x by x to get x squared, so x goes into x squared x times. What do I need to multiply by x to get x cubed? X times x squared is x cubed. So if I'm going to cancel this x, and I know I have to do it in both terms, what do I need to multiply this x by to get x squared and to get x cubed? Now that I've made that determination, I can rewrite this problem as 2x squared minus 3x over 1. 1 times 1 is 1. Of course, I don't need the over 1. If that's really all that's left in the denominator, then I don't need to write it. Now let's do the same problem using long division. 5x goes into 10x cubed. How many times? Another way to think of this is, what do I need to multiply by 5x to get 10x cubed? Well, 2 times 5 will give me 10, but what times x gives me x cubed? X squared times x will give me x cubed. Each time I do one piece of a long division problem involving polynomials, I'm going to be asking myself, what do I need to multiply by this to get this? That is the answer to that question. Then when I do this multiplication, I take all of this, multiply it by all of this, and that gives me this here. When we do long division of polynomials, you'll soon see that what you want is for these two terms to be the same. That way, when you subtract them, you end up with 0. And you can bring down the next term and carry on. Okay, let's keep going. We've determined that what I need to multiply by 5x to get 10x cubed is 2x squared. Doing that multiplication, I get 2x squared times 5x is 10x cubed. Now that I've written that down, I'm going to change the signs and add. 10x cubed plus negative 10x cubed is 0. Then I can bring down the next term, minus 15x squared. I don't need to write the 0, and I'm ready to go again. 5x goes into negative 15x squared, means what do I need to multiply by 5x to get negative 15x squared. Something times 5x equals negative 15x squared. What is the something? Well, the number part is going to be negative 3 because negative 3 times 5 is negative 15. The variable part is going to have to be x because I need an x to multiply by an x in order to get x squared. Here's a good example of why it's helpful to think of changing the signs and adding instead of subtracting. If you think subtract negative 15x minus negative 15x, are you going to write down 0? Or are you going to write down negative 30x squared? When you subtract, well, isn't this already subtraction? Shouldn't we just add these two together? If you get in the habit always of changing the sign in the second line here and adding the result, you're much less likely to make this addition error. I have a remainder of 0. Notice that my answer here is the same as my answer here. This changing the sign and adding is going to come up over and over and over again. And I'll keep reinforcing it, and I would encourage you to use that technique. Of course, I can't mandate it. I can't tell you that you must change the signs and add. You're welcome to think of subtraction instead. But I'm here to tell you, if you change the signs and add, there's a lot better chance you'll get the right answer in the next line. This one's a bit more complex, but we can set them up the same way. To do this problem in its fraction form, I need to cancel 8 with 24, 16, and 4. 8 goes into 8 once, 8 goes into 24 3 times, 8 goes into 16 twice, and 8 goes into 4. Oh, wait a second, 8 doesn't go into 4. 4 goes into 8, but not the other way around. I can't cancel the 8. I can reduce what does go into all 4 of these. 8, 24, 16, and 4. 4 does. 4 goes into 4 once, 4 goes into 16 4 times, 4 goes into 24 6 times, and 4 goes into 8 twice. Another way to think of these is what? Another way to think of this is 4 times what gives me 8? 4 times what gives me 24, and so on. It's handy that we can think of that way, because now I need to do the x's. X squared goes into x cubed. If you can see that that's x, that's great. But if you can't, you can always think, what do I need to multiply by x squared to get x cubed? What do I need to multiply by x squared to get x squared? 1. So x squared goes into x squared once, and x squared goes into x cubed x times. If I'm going to cancel x's, I need to do it in all 3 terms. This plus sign and minus sign tell me that's the case. I've already canceled in one term, but let's see if we can reduce or cancel in the other 2 terms. What do I need to multiply by x squared to get x squared? 1. What do I need to multiply by x squared to get x squared? 1. In other words, x squared goes into x squared, it goes into x cubed, it goes into x squared. Finally, what do I need to multiply by x squared to get x squared? 1. All right, what about the y's? I have 1 copy of y down here. So if I cancel this one, and it's the only one I can cancel in the denominator, then I'm asking myself, how many times does y go into y? Once. Or what do I need to multiply by y to get y? And the answer is 1. What do I need to multiply by y to get y squared? Y. What do I need to multiply by y to get y squared? Y. And what do I need to multiply by y to get y cubed? y squared. It's not really very obvious anymore, but there's still a plus sign here and a minus sign here. And I'm going to rewrite those just to make sure I don't forget about them. And finally, I can rewrite my answer. Cleaning things up a little bit, I get 6xy plus, now can you see why I rewrote that? 4 times 1 is 4, and 4 times y is 4y, minus 1 times 1 is 1, and 1 times y squared is 1y squared, or if you prefer, just y squared. This is all over 2 times 1 times 1, which is 2. All right, let's have a go at the long division version. What do I need to multiply by 8x squared to get 24x cubed y squared? We can break this down into 3 parts. What do I need to multiply by 8 to get 24? That, of course, is 3. What do I need to multiply by x squared to get x cubed? And that's x. What do I need to multiply by y to get y squared? And that's y. Okay, now that we've determined this, we need to do our multiplication. 3 times 8 is 24. X times x squared is x cubed. Y times y is y squared. Now I'll change the signs and add. 24x cubed y squared plus negative 24x cubed y squared is 0. I don't need to write the 0, and I'm going to erase it in any case. So let's just leave it out. But now I can bring down the next term, which is a positive 16x squared y squared. And then the process starts over again. I'm looking for the term that when I multiply this by this, I get this. So what do I need to multiply by 8 to get 16? 2. Positive 2 specifically. Notice that there's a sign here, so I need to put a sign in between these two terms as well. What do I need to multiply by x squared to get x squared? 1. Well, 2 times 1 is 2, so I don't need to write times 1. Now the y's. What do I need to multiply by y to get y squared? Y, because y times y is y squared. Now that I've determined that this is the thing I need to multiply by 8x squared y to get 16x squared y squared, I need to do that multiplication. 2 times 8 is 16. There are no x's here. It's like saying times 1. 1 times x squared is x squared. Y times y is y squared. Change the signs and add. And once again, I get 0. Now I can bring down the next term. Notice that it's preceded by a minus. I need to bring that down as well. I didn't put a plus here, although I could have. We know that when there's no sign in front, it's implied that it's positive. There's no plus here either, but I knew that was positive. And now the process starts over. How many times does 8x squared y go into negative 4x squared y cubed? Well, what do I need to multiply by 8x squared y to get negative 4x squared y cubed? What do I need to multiply by 8 to get 4? This is tricky. It's a half. And don't worry, I'm using this example because it's in the textbook. Even though they don't do it this way, I wanted you to see that you could still do it this way. I won't give you long division problems where you get a fraction up here. You may see them in the future, but you don't need to worry about them in this class. So 1/2 times 8 means 1/2 of 8, and that's going to give me this 4. But I have a positive 8 and a negative 4. So I need to ask myself, what sign do I need here so that when I multiply it by positive 8, I end up with negative 4. And that's a negative. Negative 1/2 times 8 is negative 4. What do I need to multiply by x squared to get x squared? 1. Well, 1/2 times 1 is still just a half, so I don't need to write the times 1. And what do I need to multiply by y to get y cubed? That's y squared. So this is my answer, and it looks different this time. There's a reason for that. It's really just a case of formatting. I could rewrite this fraction as 6xy over 2 plus 4y over 2 minus y squared over 2. If I had 5/7 plus 11/7, and I asked you to add those together, hopefully you'd say, well, that's just 5 plus 11 over 7. Except instead of going this way, I went this way. I took a fraction with a sum in the numerator and changed it back into the sum of two fractions with a common denominator. I took a fraction with a sum in the numerator and changed it into the sum, or difference, of fractions with a common denominator. So all I'm doing is this adding together of fractions, but backwards. Now, I could write 6 over 2 as 3, and 4 over 2 as 2, and that lets me change this to 3xy plus 2y minus y squared divided by 2 can be thought of as half of y squared. So 1/2 y squared. That answer does match this one. So even though they don't look the same, these two things are equivalent. You can do these problems either way. In this class, this is by far the most complex of this type of problem that you'll see, at least where we're dividing by a monomial. When we go into section 5.8, things get a little bit more interesting because I'm going to be dividing not just by a monomial, but by a binomial. But that's for the next section.